All right. What's going on, guys? Today I'm going to be briefly discussing intermolecular forces. All right, so I'm in my first week of organic chemistry lab, and we're just doing some review on intermolecular forces and other stuff like that. But I just want to briefly go over some of the big key players in our intermolecular forces topics. Okay, so the first one that I want to talk about is dipole interactions. To start, these are the strongest kinds of interactions that a molecule or molecules can show. An example of a dipole interaction is something like HCl and another HCl. So it looks something like with slightly positive charge on the hydrogen and that slightly negative chlorine, taking over those electrons, want to hoard them. And yeah, basically like this interaction right here is called a dipole-dipole interaction. In order for something to qualify as like a dipole-dipole interaction, there has to be a net dipole movement between polar molecules. So polar molecules have an electron poor and an electron rich area, which is why I showed this little diagram of like the electrons being sent. Like, all right, we got electrons over here, and then there's like one, the electron poor being the hydrogen, and then yeah, that's pretty much it. In addition to this, as the net dipole movement increases, my intermolecular forces are going to increase. So like the more polar, the stronger the bonds or interactions. And it's not a bond. Okay, next up, we have dipole-induced dipole. Okay, this guy's a little bit different. This time we're looking at polar and nonpolar molecules. So basically, a dipole-induced dipole is when you have an already polar molecule that's going to react with a nonpolar molecule. So you basically have you start off with like a uniform distribution of charge. So like just for example, we got some like plus, plus, and then, I don't know, minus, plus, plus, minus, minus. I don't know. I don't really know how to describe that. But basically like it's pretty, actually that's not very uniform. Here, I'll just do it like this. Okay, I guess that makes sense. So this is going to be like our non-polar, because all the charges, kind of cancel out. There's no net charge, blah, blah, blah. And then you got something like, for instance, water, which as we know is a polar molecule. Who would have guessed that? Me. I would have guessed that. With this little negative charge over here on the oxygen in comparison to our hydrogens. Okay, so basically what happens is these guys kind of like bump into each other, and then our originally non-polar molecule kind of orients itself. So let's say that like we got our little hydrogen here. Okay, so basically we know this is like a slightly positive charge. You're going to get most of that negative charge is going to want to go to this side, and then you're going to get like the name suggests, induced dipole. That's pretty much it. In regards to strength, as the polarity increases, the strength will increase. And then in contrast, the polarizability of the nonpolar increases will lead to a greater interaction strength. So like the more polarizable the molecule is, the easier it's going to be to make, or the stronger the interaction is going to be. Okay, last but certainly not least, I want to go over something that you guys have probably heard of. London dispersion forces. Also known as induced dipole, induced dipole. Okay, so basically you're going to find these London dispersion forces when you basically make two molecules interacting with each other have like a temporary dipole moment. So we're basically going to have like a symmetrical distribution, but then when it gets next to something, it's going to have an asymmetrical distribution. So let's say we start out with our atom 1 looking like boom, 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 boom. And then when it's popped up next to another one of these guys, there's a pretty significant, little induced dipole action. Okay, so a little bit more on this. You're probably going to need to know, or at least I need to know, like the strength in regards to like carbon chains. So if I have a carbon chain, let's say I have a little butane action. Butane action. Basically, what you need to know is as the surface area of this molecule increases, the London dispersion force's strength is going to increase as well. So like, let's say relatively speaking, I'm just going to pull some random numbers. This has got a strength of like 1. This guy, since there's some more carbons on there and a greater surface area, I'm going to give him like a 2. However, there's a little caveat to this, because if I have something that looks like, like this, got a little methyl on there, that's actually going to make the strength go down. So I'm going to say like 1.5. Actually, no. I'll do like 0.8. These are just random numbers pulling from nothing. Essentially, in the textbook, it uses boiling point. So like this, I'll do a different color for that. This has a boiling point of like 0 degrees Celsius. And then this one has like a boiling point of 36 degrees Celsius. And then this one's like 28 degrees Celsius. Okay, so I guess this is like a little bit stronger than 1, but not as significant as having like another carbon. So like 1.5, whatever. Yeah, I think that's pretty much it. There's not much more I really want to cover. Yeah. That pretty much does it. That's a really brief overview of some intermolecular forces. Thanks for watching, guys. Bye.